Hi class. In this section 2.4, we're looking at a special type of equation called exact equations. So we're going to start off talking about not differential equations. Then talk about, say you have some sort of function of two variables, x and y, that is equal to a constant. And this might be, you see these like on weather maps and level curves, that sort of thing. And so as I do all this stuff, I'm going to do an example um, to make it sort of concrete. And so an example of a level set type of function that you might be used to would be something like x squared plus y squared equals r squared, right? A circle. And this circle exists in the xy plane. And so you usually think of functions y that are a function of x that depend on x. But oftentimes, in the case of a circle, it's easier to rewrite that um, as this function of two variables. But you still might be interested to know the slope of the tangent line to that circle, which would be the derivative of y with respect to x, just because it's rise over run in the xy plane. And so same thing with a general curve f of xy equals c, we might want to know the derivative with respect to x of f of xy. And so that's going to be the derivative of d dx of the constant c. And the way that you define the, or the way that you find the derivative with respect to one variable in this function of two variables, this is a result from multivariable calculus that I'm not going to go into in great detail, but of course it involves partial derivatives. So I'm going to take the partial derivative of f with respect to x, plus now when I take my derivative with respect to y, since I ultimately want to know what the derivative is of this function with respect to x, I also need to know the derivative of y with respect to x, and I kind of multiply through this way. And then on the right-hand side, the derivative of a constant is 0. So in our example, we can do that. So we want d dx of x squared plus y squared equals d dx of r squared. And then if I take my derivative with respect to x, I get 2x plus 2y, that's my derivative with respect to y, times y prime, and then the right-hand side equals 0. Now, over on the general case here, let's try to solve for our slope, which is dy dx. And that's going to be our partial, let's see, negative, our partial of f with respect to x divided by our partial of f with respect to y. And we can see the same thing over on the right-hand side. We're looking for y prime by itself. So we get our 2's cancel and we get negative x over y. So since I didn't really prove um, the details of what I did over on the left-hand side, the point of this example on the right-hand side is to just sort of demonstrate to you that this makes sense. So if you have a circle, um, like let's say the unit circle, 1, -1, and you want to know the slope at any particular point. So let's say this point is, this is going to be rad 2 over 2, comma rad 2 over 2. And then the slope would be, of course, we know the slope of the tangent line is -1 at that point, and we can actually plug it in, negative x over y equals negative rad 2 over 2 over rad 2 over 2 equals -1. And then same thing, let's see, right here, of course, we know the slope should be 0, and this point is 0, -1, and then the slope equals negative x over y, which equals 0. Of course, you run into problems at the vertical slope, but you always run into problems there. So anyway, let's go back to our left-hand side. And remember when we did separable equations, I told you that even though it seems really wrong to treat dy and dx as quantities, that we were going to do it anyway and rely on faith that there was solid mathematics to back us up. And so that's what I am going to do now. So this equation here, this last one that we've been working on, we can rewrite by, cross multiplying and then adding the terms over to the same side. And we end up with df dx times dx. So our partial of f with respect to x plus our partial of f with respect to y dy equals 0. And this quantity here is called the total differential of the function big F of xy. And all of this is, like I said, this is business from like multivariable calculus and other things that is not actually, that doesn't actually like matter here because we don't care about finding the slopes of tangents to level curves and that sort of thing here. However, why this is useful is that sometimes if we have a differential equation that kind of takes a form like this, then this gives us a way to solve it. And that's the point of what's going on here. So another way to say that is if we have a differential equation that looks like this over here, if it is some expression where equals 0 and the left-hand side is the total differential equation, or if is the total differential of a function, of some function big F, then we know how to solve it because then we can just work backwards and then our solution will be given implicitly by this equation f of xy equals c, and then maybe we could solve for y in there. So now what we need to know is a way, if we're given a differential equation, can we determine whether it is the total differential of some big function f of xy? And so let's write that down as a definition, and then we'll find out how to solve it. So here's our definition. If there's some function big F of x and y, where its total differential is where its derivative with respect to x and its derivative with respect to y put together make this differential form appear. We say that differential form is exact, okay? And we haven't really talked about what differential forms are, but you can think of it just as the sort of left-hand side of a differential equation where you set that form equal to 0. So when you see something like this, in the homework, you'll see these problems that look like, something something dx plus something something dy equals 0. That's an exact equation if there's some function, big F, where the n is the derivative of f with respect to x, and the n is the derivative of f with respect to y. Okay, so that's what you would have to check. Now let's see an example of that. Here we go. We've got a differential equation. We've got our y prime equals some function of x and y. And I want to write this in, I want to see if this is an exact equation. So I'm going to write it in a differential form. So first of all, we can think of this y prime as like dy dx. And then we can move that dy dx around. And there's a few different ways that we can do it. And some ways that we do it might give us an exact differential form, and some ways might not. So a couple of different ways we could, let's see, we could write this as first one. The first one is kind of the obvious one if you cross multiply and then add over, so you get 2xy squared plus 1 dx plus 2x squared y dy equals 0. That's an equivalent way to write this equation that we're interested in. But you also could sort of write them a couple other ways. So this would be another way. Put everything in front of the dx. So I'm just sort of doing some basic manipulation. And you could also put everything in front of the y if you wanted to. So now the second and third ones may or may not be exact equations. But I am here to tell you that this expression here is the total differential of the function f of xy equals x squared y squared plus x. And in fact, you can check that partial of f with respect to x equals 2xy squared plus 1, which is this bit right here. And the partial with respect to y is going to be 2x squared y, which is this right there. Okay, so that's what it means to be a total differential. So that's just the sort of giving you the definition. I'm not telling you how I found that, but now that I know that this equation, that really the equation that we're looking for up here, rewritten in this way, is an exact equation that I can find this function big F, that tells me how to solve it. Because as we saw in the discussion at the beginning, having level sets of some function f of x, y, you can sort of basically take the derivative of both sides and you get your total differential equal to 0. So this tells us that the solutions to the exact equation are given by f of x, y, which in this case is x squared, y squared plus x equals a constant. So these are implicit solutions, but that's fine. So that's, if we can find the total differential associated with an exact equation, then we know exactly how to get the solutions to the equations. We just set that function big F equal to a constant. So now what would be nice to know is a way to tell if an equation is exact. And so assume that it is. So assume that you've got an exact equation. Okay, so assume you have an exact equation, and these coefficients, these m and n functions, assume that they have continuous partial derivatives. Okay, so what would then have to be true in order, like, what does this say about what that function f would end up looking like? Well, we know that the partials of f equal m and n. So we have df dx equals m, and df dy equals n. Okay, that's the definition of being exact. Now, you may have seen in calculus before that under appropriate conditions, you can take mixed partials in any order. So that means that if you take the partial derivative with respect to x and then y, that's the same thing as if you take the partial with respect to y and then x. Okay, so let me write that out. So up here in this line, I've already taken a first partial of f. So if I then take this one and take the derivative with respect to y, that should be the same thing as if I take this one and then take the derivative with respect to x. So what this should imply, if we have our mixed partials are equal, then that should imply that dm dy should equal dn dx. So if our equation is exact, then this thing is going to hold. And as it turns out, you can actually make it the other way. So if this condition holds, it is also true that our equation is exact. Okay, and so we're going to prove that now and state it as a theorem. So here's the statement. We're going to assume that our m and our n have are continuous and have continuous first partial derivatives, and that will satisfy the continuity conditions that I referenced earlier. Okay, so assuming that your m and your n are sort of nice enough, then this equation right here, which we're going to call EE, that's written in this differential form, this equation is an exact equation if and only if this compatibility condition, CC, holds for every x and y in the rectangle in sort of the domain that we care about. Okay, so that means in order to prove this, we have to show two things. We have to show that if EE is an exact equation, then that implies the compatibility condition holds. Okay, so we already showed that. So we already showed that if EE is exact, then CC holds. But this if and only if means that these two things, the equation being exact and the compatibility condition holding, those are true at the same time. Okay, so we have to prove the other direction now, that the compatibility condition implies that our equation is exact. So we will assume the compatibility condition CC holds. And what we need to do is need to show that EE is exact. And what does that mean? It means that we need to find a function big F where the left-hand side of EE is the total differential of big F. And what's going to be really nice about this proof is not only that we're going to, like the way that we're going to show that EE is exact is by actually constructing that big F. So then once we've constructed the big F, we'll even have a solution to our differential equation. So that's going to be really nice. So what must, I don't remember if I've used this term before, but the big F we call a potential function. What must the potential function big F look like? Well, first we know that the first derivative of f with respect to x is, or the partial derivative, we know that this equals n. Okay, so if that's true, then we can integrate with respect to x. So we're going to integrate with respect to x, and that'll give us that f of xy equals the integral of m dx plus a constant, but that constant could have y's in it. It's constant in x, so there could be some other stuff there that has y's in it. Okay. And now that we have this, we also know one other thing about big F, which is that its derivative with respect to y equals n. So now we can differentiate with respect to y. And we know that df dy of xy equals the derivative with respect to y of this thing up here. So the derivative with respect to y of the first term is just the derivative of that integral, whatever it looks like. But then when we take the derivative with respect to y of g of y, that just equals, g prime. So I'll write it like this to be clear for right now. So we know that this thing is g prime of y, and then this thing is n, because we would need our, we're looking for a big F that makes our equation exact. And so if we shift these things around, we get that g prime of y, which is something that it's some constant, but we don't know what it is equal to n of xy minus d dy integral of m with respect to x. Okay, so that's nice. It actually gives us a way to figure out what g of y is. So what have we done? We've said we want E to be exact. If EE is exact, then it's got to have some potential function big F that has these properties, that has this property with its partial derivatives. And if that holds, then we'd also have to have sort of all this business going on. So if we need to have an F that looks like that, let's just define an F that looks like that. Okay. So let's fix a point x naught in our rectangle. And we're just going to define a function big F of xy. This colon equal sign is like I'm defining this function this way. So it's going to be the integral from our fixed point to the variable x m of t now is the dummy integrating variable. And then some function of y. And that function of y is defined by what its derivative looks like. So I know that this definition looks like weird, but I mean, it works. I've defined a function. And if we kind of reverse all the steps that we just did, then that f is the potential function for the equation. Okay. So this function big f of xy is a potential function for EE. Therefore, our equation EE is exact because there is a potential function where the total differential of that potential function is EE. Okay, and that's the end of our proof. So now let's be a little bit more concrete about how we can use this proof that was constructive. It told us how to build our potential function. How do we use this to actually solve our exact equations? So here's our method for solving exact equations. Suppose you're given an equation that might be written in this kind of differential form with the dx and the dy separately. It might not be. You might need to put it in a form like this. So the first step, if you aren't already told that it's exact, you want to check to see if the equation is exact by testing the compatibility condition that we saw before, dm dx, dm dy equals dn dx. So you're like switching, remember, because you're basically checking to see if the mixed partials are equal. Okay, so if this doesn't hold, then maybe you want to try to rewrite the equation into a different form that might be exact. Or you might just need to find some other way to solve it. So if you get no in step one, then you got to move on. You can only move on to step two if you have an exact equation, obviously. So step two, now that we know we have an exact equation, we need to figure out what its potential function f is. So if our equation is exact, then we know that the switch to blue. I don't have a good rhyme or reason why I'm using different colors, as you might have noticed. df dx equals m. So next we will integrate with respect to x. And then you get your f of xy equals the integral of m xy dx. Now, in the particular problem that you have, m will be an actual expression that you can probably just integrate. So your answer won't have an integral in it at the end. Okay. So next step, to determine what that g of y is, we're going to take our partial with respect to y of both sides. Then substitute in, so your left-hand side, if you take the partial with respect to y, you'll get df dy. So that is equal to your n, which is given to you by the problem. And solve for g prime of y. So that will be your sort of second term in the right-hand side. So step 4, if you have g prime, you can integrate it. So integrate g prime of y to get your g of y. And then you can substitute into this equation right here to get f of xy. And step 5, now you've got an f. And since you have an exact equation, you've found the f, the solutions of your exact equation are given by the level sets of your f. So solutions to the equation are given by scoot up a little bit, f of xy equals c. So once you have your f, just write f of xy equals c, and you're done. Put a box around it. All right, I'm going to make a couple of remarks now. So you could have done the same procedure if you started with n, df dy equals n of xy, and then you could have integrated everything with respect to um, to y, and then when you got your constant of integration, it would be some function g of x, and everything kind of goes the same way. You might try, doing some of the problems either way and see that they give you the same answer. And sometimes it'll happen that you have to do an integration, and one of the terms will be harder to integrate than the other. So that would be why you would choose one over another. But doing it either way should give you the same answer. And then the second remark is that the ODE, the ordinary differential equation, that is written in this kind of differential form, m of xy dx plus n of xy dy equals 0. You might instead see this like this. So you might see that equation written in a more traditional form where you have your, you know, derivative looking like the normal thing. So you have, the derivative times something with x and y plus something without a derivative term in it. And if, just like we saw in the example before, you can shuffle this around to put it into the differential form. So if you were given something in this form, you can still shuffle it around, and all those previous results about exactness are going to hold for this equation too. So you can that tells you how to figure out if this equation is exact, and if you can use the methods from this section to find a solution. So that is the deal with exact equations. And examples are nice, but this video is getting pretty long, so I think I'm going to hold off on the examples. There are lots of examples in the book that you can start practicing. You can read how they went through them, and then I will certainly do some examples in class. But we'll take a break from the video now, and we'll see you next time.